Okay, so good morning, everyone. Our first speaker today is Natanael Costa from the Federal University of Rio de Janeiro.
Good morning. First of all, thank you for having me here. I'm Natanael, and I'm from Federal University of Rio de Janeiro. And I'm going to present some results that we have been taking in our group there in collaboration with many people around the world concerning to the nature of charge density wave based on some quantum Monte Carlo simulations. I divide my presentation this way, where first I will present some a very brief introduction about the issue, more specifically the standard explanation for charge density wave, the Pyre's instability. And after that, I will present some results concerning to the effects of the Phonon dispersion. That is basically a new approach that we are proposing. And at last, I will present some results about disorder. So I hope we have time enough to discuss about all of these issues. So it's basically I divide my presentation in 3 parts. Okay, let's start with the Pyre's instability. I don't know if you know about it, but I will review it very quickly. And the Pyre's instability, the Pyre's instability is basically the standard explanation for charge ordering. It basically says that you have a kind of a recipe to create charge density wave. That it basically says that if you have one-dimensional system with that has a firm surface nesting, that this point is very, very important. I will show you why. And if you create an electronic instability or a let's distortion, then as a result, you have a charge gap at the firm level. In other words, you have a metal insulator transition. You have a Phonon softening exactly for the wave vector equal to the nesting vector, or two times the firm wave vector, and you create a less distortion. Basically, this is what the Pyre's instability says. And the reason for this is very, very simple. You can explain this why you have some these requirements based in some linear response theory. If you create a perturbation in an electronic system, you see that your electronic susceptibility has this is described by this equation. So if you have a firm surface nesting, it's basically your energy can be mapped by a unique vector. This term in the denominator goes to 0, so you have a divergence. And for instance, for one-dimensional system, for a Fermi gas, you have a logarithmic divergence in the electronic susceptibility, while in the 2D and 3D case, you don't have. So what it means? It means that your system is highly susceptible for external perturbations. It's basically that. Then, if you include, for instance, one external perturbation, like electron-phonon coupling, like here in the Fröhlich Hamiltonian, you can show that you can lead to a charge density wave based in this inequality here. So, but you have to see here one thing that's very interesting. If your electronic susceptibility goes to infinity, in other words, has one divergence, this term in the right side of the inequality goes to 0. So any electron-phonon coupling leads to a charge density wave. So this is what Pyre says. And indeed, this occurs in nature. If you see, for instance, some organic materials like this one, where you have basically two quasi-one-dimensional chains coupled weakly coupling one each other, you have based in main different measurements like STM. You can see the real space modulation of charge based in ARPS, where you see the nesting vector exactly equal to the wave vector for charge density wave. You have the Phonon softening by neutron scattering. You have metal insulator transition. Actually, here you have 2 metal insulator transitions because you have 2 chains coupled. So we have one metal insulator transition for one and then to another for different temperatures, like 55 and 38, I guess. So indeed that occurs in nature, but the nature is not what we want. For instance, recently in some materials, some quasi-two-dimensional materials, like transitional metal chalcogenites, they can show that, for instance, for this one, the niobium selenate, you don't have one divergence in the electronic susceptibility. You don't have Fermi surface nesting. That is one very required thing for Pyre's instability. You don't have metal insulated transition, even though you have charge density wave. So it's completely out of the standard explanation for charge ordering based in Pyre's instability. And the standard explanation for this kind of system is based in some line width, Phonon line width measurements, where they show that they can measure, sorry, this is a little bit cutted here, but they can measure the direct electron phonon coupling, and they see that this coupling is very high, exactly for the charge density wave vector. So what they propose here is basically you have a large, quite high momentum-dependent electron phonon coupling. So this is the standard, the proposed explanation for this kind of system. But again, the nature is not what we want. If you repeat the same measurements for instance, cuprates, you have a very large electron phonon coupling, but even though you don't have charge density wave. So what people say is here is basically electron-electron interactions should play an important role here. So charge density wave is not so simple as we have thought before. We have think before. So what we do here is basically what we have. Sorry, here is basically we have quasi-one-dimensional materials that we know that this is this behaves like Pyre's instability. We have quasi-2D materials, like, for instance, transitional metal chalcogenites, where the proposed explanation is based in momentum-dependent electron phonon coupling. And we have cuprates that we don't know what's happening here, but we believe that the electron-electron interaction should play some important role. But we are interested in other roads, alternative roads. Yeah, yes, but the point here in this quasi-2D material is that based on some phonon line width measurements, they can directly measure the electron phonon coupling, and the fact that the electron phonon coupling is very high, exactly for the same wave vector for charge density wave, people believe that this should be the Oh, sorry. Yes. Okay, good. We can talk later again. Okay, so the point is we are interested in some alternative roads. And if we look for the charge for the a naive explanation, a naive alternative roads is looking back to the Pyre instability, and we see that here, if this term in the right side is not so high, we have two terms in the left side, the electron phonon coupling and the phonon dispersion. So it's not just this term, the electron phonon coupling, that should play an important role. The phonon dispersion also should play an important role here. So what we are going to do here is try to understand what's the role of the electron of the phonon dispersion for charge density wave. This is the main this is the main topic of my talk here. Okay, we do this based in some determinant quantum Monte Carlo simulation, which is an exact approach, an unbased approach, and we don't have sign problem if you know what is it. Okay, let's discuss then some results about this. Let's introduce you the model that I'm working with. We have one lattice. In this lattice we have ions, and then I allow these ions to vibrate around one equilibrium point. So in other words, we have quantum harmonic oscillators in each side. And I have electrons, and these electrons can hop for side to side, and these electrons can interact with the ions. But for a while, I will not include the Hubbard interaction, okay? I will not include because just this model is already too complicated, too complex to reanalyze. So I will not include Hubbard interaction, but we know that because of the interaction with electron and the ion, we have indirect interaction between electrons mediated by phonons, okay? So if I write up my Hamiltonian, I have this Hamiltonian here where we have the hopping term, the electron-phonon interaction, and the local harmonic oscillators. Okay, for a while, I have like something like a Einstein model, where we have harmonic oscillators vibrating. I don't have yet phonon dispersion, okay? I will include that later, okay? Let's just discuss this part for a while. Just some physical quantities that I'll measure. I'm interested in the density structure factor, that is something related with the X-ray intensity, and the pair susceptibility that gives me the superconductivity. And this is some dimensionless parameters that I will not discuss here. Okay, let me remind you one very important thing. I'm working with the squarelets. And in the squarelets, I have Fermi surface nesting, and I have Van Hoff singularity. So here, because of these two things, I have a very, very divergent electron susceptibility, and what I expect is that I will have charge density wave Pyers-like type. Okay, so let's see what we have. For a while, I did not include dispersion. Okay, when I analyze this for the structure factor for different lattice size, I see that for one beta here is the inverse of temperature. I see that for one energy scale, this has one lattice size dependence. And for those people that work with Monte Carlo simulations, here we know that maybe we have one long range order. But I have to remind you that we are working with charge density wave. That's basically one phase that has one dimensional or one component or the parameter. I expect a finite temperature phase transition, and I'm working with a two-dimensional lattice. So I know already what are the critical exponents. The critical exponents are the same of the 2D Ising model. And then when I take these results and use I perform some scaling analysis using the 2D Ising exponents, I can get, for instance, I can take on data collapse of these results and can get the critical temperature. So okay, I have charge density wave. This charge density wave seems to be like Pyers because of the Fermi surface nesting. And if I analyze, for instance, the charge gap, I have indeed a charge gap here. When I change the chemical potential, I see that I have a plateau that is basically the opening of this charge gap here. Okay, this is Pyers type. Okay, good. So let's now proceed and include phonon dispersion. And how I include phonon dispersion? Allowing the ions to see each other, allowing the ions to push and pull each other simultaneously. So what I did is basically I include here one term like that, and this term will play the role of the ions push and pull each other simultaneously. Okay? It's important I remind one point. This term here just affects the Berry phonon dispersion. It doesn't have anything related to the Fermi surface nesting. I still have Fermi surface nesting. So in this case, as before, I should expect that the system should be charge density wave, Pyers-like. So let's see what will happen. Okay, with this new term, I have these three types of phonon dispersion. One type that we have a kind of upward concavity, this one here, a downward concavity, this is the second one, and on the third one we have different types of anisotropic interaction between ions, and then I can have something like a saddle point. These are the three types of phonon dispersion that I will work with here. So let's start with the first one. What happens if I have an upward concavity? So let me remind you that one thing that is very important for charge density wave is the charge gap. And I have shown you before that for the Pyers-like type, I have a charge gap. So when I have this kind of dispersion, and I start to increase the phonon bandwidth, I see that this charge gap starts to decrease. What means that I'm destroying charge density wave. In other words, this kind of dispersion is not good for charge ordering. On the other hand, if I have a downward concavity dispersion for phonons, I increase the charge gap, this blue one here. So, in other words, this one is good for charge density wave. I'm enhance charge correlations with this phonon dispersion here. And this is much more evident when we repeat the same procedure that I showed you before concerning the data collapse using 2D Ising exponents. And I see that, for instance, for the upward concavity case, the beta, the inverse of temperature increase. In other words, I have to assess very, very low temperatures to have charge ordering. While in the downward concavity, I enhance charge correlation, so the inverse of temperature decrease. In other words, the temperature is higher. So this is much more evident in this case. Okay, so what happens if I have a saddle point case? For a while, everything here is Pyers-like, okay? But what happens if I have a saddle point? If you think for the previous example, in one hand we can expect charge density wave because we have an maximum for some points, but I have a minimum for other points, so we can expect that the charge density wave can be destroyed. So the point is that when you have this kind of saddle point, you have one kind of staggered charge density wave for a critical value, and then you change for a charge ordering that's it's stripe-like here. We have this, and then for a critical value you have a stripe. So let me remind you that the nesting vector is pi. It's not 0 pi. It's not 0 pi. So in this case, we don't have a Pyers-like type density wave. So the phonon dispersion is enough to create non-Pyers-like charge density wave, something like we have seen in these quasi-2D materials. Okay, let's proceed and discuss a little bit more about this upward concavity. We have seen that this case is not good for charge ordering. It destroys charge density wave. So the point is, what happens if we increase more and more the phonon bandwidth? So it's possible to have, for instance, superconductivity. And the answer is yes. If you see here, for instance, the dashed line corresponds to the charge structure factor, while the solid line is the S-wave susceptibility. We see that when the charge structure factor goes to 0 or is suppressed, we have a very, very large enhancement of S-wave superconductivity. And again, in order to show that we have long-range ordering, we need again to perform some scaling analysis. But we know that we are working with a 2D dimensional lattice with a two-component for superconductivity, a two-component order parameter. So it belongs to a Kostelis-Thouless universality class. And we can, for instance, by analyzing it for one fixed value of dispersion, we can see that we have long range ordering. So summarizing this first part of the talk, what we have here is basically when you have this kind of dispersion, a downward dispersion, you enhance charge ordering, we enhance charge density wave. When you have saddle point, you can lead to non-Pyers like charge density wave. That's one thing that happens in real materials. And for this other kind of thing, this other kind of dispersion, you can have charge density wave, but if the Phonon dispersion, the Phonon bandwidth is large enough, you can destroy charge density wave and can create superconductivity. So basically, this is the first, the partial conclusion of our work. I don't know how much time I have. 9 minutes? Okay, good. I have time enough then. So let's, this work, if you are interested in more details, it was published recently in the Physical Review Letters. You can see more details, or we can discuss later. Okay, let's discuss another topic here. What happens when we have disorder? Okay, why we are interested in this kind of systems? We are interested because recently, in some high impact factor journals like Nature, it was showed that some materials what takes these materials that we are interested with, these transitional metal child cognates, they can show that the inclusion of disorder was basically by addition of manganese in the material, you can suppress the charge density wave. Here is one experimental result that they show that the X-ray intensity is pushed to the to lower temperatures, and the critical temperature for charge density wave is decreased with disorder. And by analyzing some STM results, they can show that indeed we don't have long range order. You have actually short range order. You have like charge density wave puddles instead of a true long range order. And this is quite interesting for us, because we can analyze some kind of things in our model. Moreover, we have this other kind of again traditional metal child cognates that by including some disorder, by adding some different chemical component, you can enhance the superconductivity critical temperature and destroy charge density wave. So we are also interested in this kind of problems, and in order to do it, we come back to our model. Then for a while we throw away the dispersion-like term, and we include here one term that gives us disorder. Okay, one Anderson-like disorder. And the reason why we choose Anderson-like disorders is because experimentally, the inclusion of manganese basically changes the local phase of the order parameter. So it's like a random field addition in the system. So here we do it with the straight disorder given by this number delta here. Okay, but before we proceed, we have to be very, very careful about it in a theoretical point of view, because in 70s, Inri and May showed that when you have a discrete symmetry in your Hamiltonian, that's our case, you have the creation of domain-like in your system, and you don't have when you put disorder, and then you don't have a true long-range order in this kind of problems for a dimension less than 2. So I know a priori that this behavior here, for instance, this tail or this creation of these puddles are because of this. So we have to be very careful about it when we are studying this problem in a theoretical point of view. But I still can analyze, for instance, the superconductivity, because the random field doesn't couple linearly to the order parameter, and I can still analyze the charge-charge correlations. So I can say something about the problem. And what I did here was, again, analyzing the charge-charge structure factor. I see that the charge-charge structure factor is suppressed with the increase of the disorder strength, and more, it's pushed to lower temperatures, something like happens in real materials. So here we see that we have the strong charge-charge correlations are pushed to lower temperatures. The same thing happens here, and but this is not the best approach to analyze this case. The best approach is trying to say something about the puddles. And in order to say something about the puddles, we need to analyze, for instance, the correlation length of the charge-charge correlations. And the correlation length basically is the width of the X-ray intensity. And numerically, we can measure it like by this equation here. And using these results here and calculating the correlation length, what we see is this result here. In other words, we have very large puddles for weak disorder strength, and we have small puddles because we have this parameter is low, is small, when we have large disorder strength. So here, at this point where we have, in this crossover from large to small regions, maybe we have something special here. And we can show that at exactly this point, when we suppress the charge density wave, we have an enhancement of the pairing. In other words, we have, once we destroy the charge density wave, or the charge puddles here, we allow superconductivity to survive, to appear. And this is basically what they show here. When they destroy charge density wave, they increase the critical temperature. And we see this for other results, like here, where, for instance, when we have a large disorder strength, and the pairing susceptibility has a very high dependence with the lattice size. As I told you, for someone that works with Monte Carlo, it means that we have probably long-range order here. But we're still working in this problem, and it's not finished. But some partial conclusions is basically we can identify the size of the puddles, and more, we can say some